Hello students, today we are going to solve a question from TIFR 2023. That question number is from section A, number is 24, and this is basically from nuclear physics. Subtopic is nuclear cell model. So in that question, the binding energy formula for a nucleus is provided that B is the binding energy that can be written as, you have a volume energy term that is AV into A, then you have a surface energy term that is AS a the power 2/3, and then you have a Coulomb energy term AC Z into Z minus 1 divided by a the power 1/3, and finally you have a asymmetric energy term A of A minus 2Z square divided by A, that is provided. Okay, sir. AV is the volume energy coefficient, this is the surface energy coefficient, the Coulomb energy coefficient. In general, this term used to happen minus, but in that question it is given plus. Okay, and A is the mass number, Z is the atomic number. So this is the binding energy formula. In fact, they have provided that coefficient, that AV is given as 15.56 MeV, and then you have a surface energy coefficient that is provided 17.8 MeV, then Coulomb energy coefficient that is given 0.7 MeV, and then you have asymmetric energy coefficient that is provided, that is 23.29 mega electron volt. Now you have to use this binding energy formula to calculate the nuclear mass difference between two mirror nuclei, that is carbon 613 and nitrogen 713. Okay, so to calculate that mass difference of these two nuclei by using this binding energy formula. Okay, and obviously they are basically mirror nuclei because proton number of this nucleus is 6, that is matching with neutron number of this nucleus, and proton number of this nucleus is matching with the neutron number of this nucleus. So I'll basically use this to calculate that nuclear mass difference between these two nucleus. Okay, so now according to that semi-empirical mass formula, I can write the nuclear mass of a nucleus having atomic number Z, mass number A, that can be written as Z times mass of a proton plus N times mass of a neutron minus binding energy, and binding energy that is provided minus AVA, then you have a S a the power 2/3, and then you have a Coulomb energy Z into Z minus 1 divided by a the power 1/3, and then you have a minus A of A minus 2Z square divided by A. So this is basically provided, this binding energy formula. So I'll use this to calculate that nuclear mass difference. In fact, I can write the nuclear mass of carbon 613. That can be written as 6 is the Z, so 6 MP, then N is 7 Mn minus AV, then mass number is 13, then you have a AS, mass number is 13 to the power 2/3, and then you have Coulomb term, that is AC, Z is how much? 6, so 6 square minus 6 divided by 13 to the power 1/3, and finally you have a of A minus 2Z square, that will be A is 13, 2Z 12, square is 1, divided by A is 13. Okay, and I'll assume this is your equation number 1. And similarly, I can represent the nuclear mass of nitrogen 713. I can write that 7 times mass of a proton plus 6 times mass of a neutron minus AV into 13. This is a mass number, and then you have a surface energy term, and finally you have a Coulomb energy term, that is AC, Z square minus Z, that will be 7 square minus 7 divided by 13 to the power 1/3, and again you have a asymmetric energy term that can be written as A of A by 13, because A minus 2Z square, again it will be on, because A is 13, 2Z, that will be 14, 13 minus 14 square, that will be on, and you have a mass number that is 30. So let us assume this is your equation number 2. So now I'll just differentiate this. I'll take difference from 2 to on, and I'll get that required mass difference. So basically, if I subtract equation 2 from on, that will provide you the nuclear mass of nitrogen 713 minus nuclear mass of carbon 613. And that can be written as, now you can see that 7 MP minus 6 MP, that will be your MP. And then you have 6 Mn minus 7 Mn, that will be your Mn. Now you can see this volume energy term, that will be cancelled. Then surface energy term, that will again be cancelled. And this term, asymmetric energy term, that will again be cancelled because they have similar sign with same magnitude or same amount. So if you subtract that, they will be cancelled, only that Coulomb energy term that will be survived. Now you can see from here that Coulomb energy term, you have AC divided by 13 to the power 1 by 3. That will be common. Now inside bracket you will have 7 square minus 6 square minus 7 plus 6. Okay. Then you have MP, then minus Mn, and then AC that is provided, or I'll write later, AC divided by 13 to the power 1 by 3. Now if you see here, 7 square minus 6 square, that will be 13 minus 7 plus 6, that will be minus 1. So 13 minus 1, that will be 12. Okay. So now that maximum student that made mistake in that question because they have taken mass of proton and mass of neutron same, and they actually obtained wrong option. But in reality, the mass of a neutron is slightly higher than mass of a proton because of its composition. It made up of it made of 2 down quark and on up quark, where proton is made up of 2 up quark and on down quark. And generally, down quark is heavier than up quark. As a result, the mass of a neutron is slightly higher as compared to proton. Now, if you substitute that actual mass, it will be like 938.28 in terms of mega electron volt. On the other hand, mass of a neutron, that is 939.57. Okay, so this is every mass I am writing here, that is in terms of in the unit of mega electron volt. And then you have a AC that is provided 0.7 mega electron volt into 12 divided by 13 to the power 1 by 3. And obviously that unit here, it will be in the unit of mega electron volt. Now if you calculate it, you'll basically get 2.62 mega electron volt. So this is the mass difference between these two mirror nuclei if you use that binding energy formula with given data. Okay, thank you very much.